Hello, I am Sourav Bhattacharya from Samsung AI Center, Cambridge. In this video, I'm going to present our work on countering acoustic adversarial attacks in smart home devices. Voice controllable devices such as Amazon Alexa, Google Home have started pervading our lives. Moreover, tiniest wearables and IoT devices are becoming speech aware. Often these voice-enabled devices are connected to various sensor actuators in the home, and the user can switch on the light or stop the washing machine by a single audio command. However, we consider a situation when an adversary plays a low-volume audio which, when superimposed with the original user's voice command, can trigger a completely different behavior, such as opening the garage door, which can potentially be harmful. This is possible mainly due to the existing vulnerability in the deep neural networks that is responsible for recognizing the voice command. In this work, we focus on a class of deep neural networks that are compressed and can be run entirely on the device without requiring any cloud support. We study the vulnerabilities of various compressed models in audio recognition tasks. We present a new training approach to mitigating adversarial vulnerabilities of compressed models, and lastly, we validate our approach with a large number of simulation and real-world experiments. As we focus on on-device deployment of deep neural networks, it requires a drastic reduction in the overall number of parameters as well as computations for efficient runtimes. At the same time, we want the compressed models to generalize well, not only for variability in human speech, but also to asynchronous arrival of adversarial perturbations and background noise and various signal distortions. To achieve all these, in this work, we present a new training approach for making compressed audio models robust. In particular, we introduce randomness in model parameter space while learning a compressed representation of audio neural networks. Next, we combine consistency and adversarial losses in addition to cross-entropy loss. And finally, we adopt an ensemble approach during inference for increased robustness. In this work, we mainly explore convolutional neural networks where the model parameters are distributed between convolutional kernels and fully connected layers. We consider end-to-end models that directly operate on raw audio measurements in addition to more traditional audio models that operate on log-mel spectrograms. As exemplary audio recognition tasks, we consider speech command recognition and ambient audio type recognition. The overall idea of adding stochasticity is as follows. Let W represents either convolution kernels or fully connected parameters of a layer. A common technique in neural network compression is to replace W with a low-rank approximation using singular value decomposition. SVD generates three matrices, U, sigma, and V. We introduce randomness by adding noise to the diagonal elements. Our training process generates a single model with fixed values for all trainable variables. During inference, new noise values are sampled, which makes slightly different instantiation of the model architecture. Final output is computed by aggregating the outputs of all models. The details of the training process, especially how we combine consistency loss, cross-entropy loss, and adversarial loss, can be found in the paper. In our first set of experiments, we measure error rates of a number of audio models under adversarial untargeted and targeted attacks. We found that both compressed and uncompressed models trained typically with cross-entropy loss remain extremely vulnerable, which is observed by their extremely high error rates. Next, we compare a number of approaches proposed mainly within the image recognition community and show that for small epsilon neighborhood, our proposed training approach generates models that exhibit much superior adversarial robustness. To understand further the effect of our proposed training process, we plot low-dimensional representations of the loss surface in the vicinity of a training data point. We observe that the robust compressed models generates much smoother loss surfaces than models learned with just cross-entropy loss. Next, we show that a small number of ensembles, for example around 3, is required for good quality inference supporting on-device deployability. Lastly, we perform real-world over-the-air adversarial attacks considering two microphones with varying qualities and different locations of the adversary and the legitimate user. We found that adversarial attacks have high success rates. When robust compressed models are deployed, we observe on average 17% relative error rate improvement. In summary, typically trained audio models are extremely vulnerable to adversarial attacks. Adversarial audio attacks successfully transfers across model architectures and input representations. We found that the degree of smoothness of loss function in the vicinity of a data point correlates well with adversarial resilience. Incorporation of consistency and adversarial losses during training results in greater smoothness. Use of small ensemble of models during inference improves the overall robustness of models. If we allow larger neighborhood size, the audio models become vulnerable to adversarial attacks. Lastly, real-world factors like synchronization, ambient noise, and environmental distortion of audio remain very challenging while building on-device robust audio recognition systems. Thank you very much.